In Module 3 of Chapter 11, we're going to look at real-world option pricing. I commented in the prior module that you can price an option in theory using risky returns on the stock, but it requires you to know some parameters that we only know in theory, we don't know in practice, but we'll see that the price we get, assuming risk neutrality and P-star, is exactly the same price as what we would get using a risky return and the real-world probabilities P. So this module summarizes a good part of what's in Appendix A, as well as references in the chapter. So the question we start with is option pricing consistent with standard discounted cash flow calculations, where we reflect the actual probabilities of outcomes and the actual risky return that the market demands. So let's imagine that we know that our stock has a continuously compounded expected return of alpha. So alpha might be 10, 15, could be some percent. If P is the true probability of an upstate, then in our binomial model, we would have this equation that says that the expected return is e to the alpha h. Right? If I divide both sides by s, on the left-hand side I get the expected return under P, and on the right-hand side I get e to the alpha h. That's the meaning of alpha being the continuously compounded return. So if we solve this for P, we get a formula that looks familiar, that the probability, once the investor identifies what U and D are in this binomial model, P and alpha you can think of as a pair. That any determination of alpha provides a P, any value of P implies an alpha. So using P, the actual expected payoff on the option would be this. Right? We have a formula for P we derived a minute ago. And so you'll notice that this is not a risk-neutral present value. This is the real-world expected payoff of the option. So now the question is, this is the real-world expected payoff at time t plus h. How do we get that back to time t? What interest rate do we use to discount it? The beauty, jumping ahead, of risk-neutral pricing is that if I use a risk-neutral probability P star, I can discount with the risk-free rate. If I'm using the real-world probability P, this is now a risky expected return. I cannot discount that with a rate of R. I also cannot use alpha. Alpha is not the appropriate return on the stock. It is the appropriate expected return on the stock, but it's not the appropriate risky return on the option. It's really the risky return on the option that we need to discount this expected price. So why isn't alpha the risky return on the option? And the answer is, an option is a leveraged investment. You remember in our earlier work, we saw that an option was a portfolio of stock leveraged by some short T-bills. Or I should say a call option is a stock portfolio leveraged with some short T-bill positions. If we looked at a put option, it would be a short stock position and a long T-bill position. In either case, the option is a leveraged investment in stock, and as a leveraged investment, it is riskier than the stock. So one expects that we will conclude that the return on the risky return for the option will be bigger than alpha. So let's denote the risky return on the option by the symbol gamma. Well, because the option is a portfolio of stock and treasuries, the expected return on that comes from the expected return on the stock and the T-bills weighted by their respective components in our replicating portfolio. And you can see that here. The price of the option, you recall, is S delta plus B. And we have S delta of that invested in stock and B of that invested in T-bills. So the expected return on the option is a weighted average of the expected return on the stock position and the T-bill position using the appropriate market value weights. Now, it's important to note that this is a theoretical calculation where we're going to show that if we knew by some method what delta and B were, we will show that the price we get by this method is the same as the risk-neutral price. But this is not a methodology that's really appropriate in practice, because when we get to this step, we have no way of calculating gamma without knowing the price of the option and the value of the replicating portfolio. So in a sense, this is a theoretical calculation that says, let's price the option using risk-neutral pricing, then we get gamma and B. So what this argument boils down to is that if you price the option with the risk-neutral probability and determine delta and B, and use that value in this calculation to determine gamma, when I price the option with gamma, I'm going to get the same price. But notice that in practice, I have this technicality that I can't actually implement this approach because I will not know the delta and the B.